Hey everybody, I hope you guys are doing well. I'm going to be giving my presentation on Gröbner bases. This is going to be part 2. So part 1 was done by Tony Lee. I'd recommend that you go and watch that one first. But I am going to try and make this presentation as self-contained as possible. So if you haven't seen it, you'll probably still be fine. There will just be some propositions and lemmas that we use that won't be proved here. Okay, so what we're really going to start with is we want to think about the ideals of a polynomial ring over a field. And it'd be nice to know, for instance, a good way of representing any arbitrary ideal over one of these rings. And to do that, there's a few things that would be nice to know, such as whether or not it's finitely generated, what the functions that generate it could look like, etc. And that can make it a lot easier to deal with the ideals. So the first thing that we're going to do is try and prove some of those nice properties about this ring that I'm going to call K for the rest of the presentation. And that's just going to be any field, a polynomial ring over any field, I should say, with n different variables. And this is going to be called K for the rest of the presentation. And we want to look at a couple ideals that we know exist in this field from the previous presentation. So the main one, if we want to start with the definition for this one important ideal, this is going to be called the leading term ideal. So if we let I be any ideal in K, then we call this set, LT of I, the leading terms of I, is the set of Cx to the alpha, such that Cx to the alpha, or such that, there exists an F with leading term of F equal to Cx alpha in our ideal I. So there exists F in I, I should say. Okay, and then the ideal that we get from this is just a set, this isn't necessarily an ideal, but we can talk about just the ideal generated by this set. And in fact, this ideal is going to be really important in proving a bunch of really nice properties about this polynomial ring. The first important property is that this thing is what we'd call a monomial ideal, which means basically it's generated only by monomials. So in fact, more than just that, we have, so the ideal generated by the leading terms of an ideal is a monomial ideal. And in fact, there exists G1 through GT, all in I, such that the ideal generated by the leading terms of I is equal to the ideal generated by the leading terms of these polynomials. So the leading term of G1 all the way through to the leading term of GT. So I'm not going to prove this here, because I think it relies too heavily on things from the previous presentation, but basically these properties are going to let us do some really nice things. And the first really nice thing that we're going to be able to prove with this is called the Hilbert basis theorem. Okay. So what the Hilbert basis theorem says is that basically every ideal in K is finitely generated. And this is a really nice property for a ring to have. It's going to make the ideals much easier to work with. So we're going to want to try and prove this. And we're going to prove it in a way that even constructs a particular generating set for the ideal. So first we're just going to take the trivial case. If I is 0, then the empty set is a generating set, which is finite. And I equals the ideal generated by the empty set. So let I be non-zero in K. And that means that we can build the leading term ideal from this. And by the previous proposition, we know that this is going to be equal to the ideal generated by the leading terms of some finite set of g's in I. The leading terms of some finite number of g's in I. And here we have gi is in I. Okay, so what we want to show is that in fact these gi's generate the ideal itself. So we're trying to show that I is in fact equal to the ideal generated by g1 through gt. So we're going to do this by doing containment both ways. First we're going to show that g is contained in I, which is, or sorry, not g, but the ideal generated by these g is contained in I, which is pretty trivial since each of these g is in I. That means that the whole ideal has to be in I. Because this is the smallest ideal containing these things, and this is another ideal containing them, so that containment has to follow. Since gi are in I. And then the other direction can be a little bit trickier. So we're going to have to use the division algorithm here. So if we want to show that I is contained in the ideal generated by g1 to gt, then we're going to take an arbitrary f in I, and we're going to apply the division algorithm by every element of this set. So that gives us, I'm going to move over to here. So that gives us that f equals q1 g1 plus q2 g2 all the way through to qt gt plus r. Okay? And now all that we need to show is that r is 0, and it follows that this function is in the ideal. Okay. So this follows from basically some propositions from the first presentation. But basically, if r is non-zero, then we know that the leading term of R has to be an element of the ideal generated by the leading terms I, which is, as we said before, the ideal generated by the leading terms of each gi. Okay, and by a proposition from the first presentation, this implies that the leading term of R is divisible by LT, or the leading term of GI for some GI. But because of basically the definition of the division algorithm, this can't happen. Okay. And that implies that R is 0. So F is in the ideal generated by each of the G's. And thus this containment follows, and the ideals are, in fact, equal. And that gives us that we have a finite generating set for I, which is what we were looking for. Okay, so checking real quick to make sure that everything's recording. Okay. So now that we've established that we have a finite generating set for any ideal in this ring, it could be nice to know if there's like a standard generating set, some sort of thing that we know will always exist and has more nice properties. And that's where the idea of Gröbner bases comes in. So now I'm going to actually define Gröbner bases. So a finite subset G of an ideal is a Gröbner basis if it satisfies the following. And that is that the leading terms of each of the G, or the ideal generated by each of the leading terms, is equal to the ideal generated by the set of leading terms of I. And we're going to use the convention that a Gröbner basis for the zero ideal is just the empty set. So this is the definition that we're going to be using for Gröbner bases, but we haven't actually shown that something that satisfies this property is a basis at all. So first we're going to try and do that. So here's a proposition. And this proposition is going to say that every ideal in I, or every ideal in K, both has a Gröbner basis and a Gröbner basis is in fact a basis. And this actually follows pretty directly from our proof of Hilbert's basis theorem, because what you might notice is that the basis that we constructed for our original ideal, the G's, also satisfies this property that the leading terms generate the leading term ideal. And that was basically by construction, because we actually started with this because we know that something like this exists, and we showed that it satisfies that the G's form a basis for the ideal. So that gives us existence. And then the fact that they are a basis is literally just the second part of the proof, where we showed that, in fact, I is equal to the ideal generated by each of the GIs. So that follows pretty directly from our proof of Hilbert's basis theorem. Okay. So now we can observe another nice property about these, or about this ring K, going off of the Hilbert basis theorem and the existence of Gröbner bases. Okay, and this is the ascending chain condition. So we have a theorem, and all this theorem says is that K satisfies the ascending chain condition. in the ascending chain condition basically says that if we have any infinite chain of nested ideals, so if we have ideals I1 contained in I2, contained in I3, going on forever, then there has to exist an n where in is equal to in plus 1 and so on. Basically, any sequence of nested ideals has to end somewhere. It can't just keep getting bigger forever. Okay. So let's prove that our ring K satisfies this. So first, we just want to start by saying we have some sort of ascending chain of ideals, and we want to prove that it terminates somewhere. So we're going to do this by defining a new ideal, and we're going to say that this ideal I is equal to the union from I equals 1 to infinity of each I in the ascending chain. So now we're going to show that this is actually an ideal. So pretty clearly 0 is an I, since each of these is an ideal and contains 0. And now we're going to let F and G be an I. I'm actually going to do this over here. So we're going to let F and G be an I, and we're going to let R be an K. So since F and G are both an I, that means that F is in I sub I for some particular I, and G is in I sub j for some j. Now, without loss of generality, we're just going to say that j is greater than I, and we can do that because they're arbitrary, it just doesn't matter. Okay. And now, since this is a chain of nested ideals, this means that F is also contained in ij. So since F is an ij, and G is an ij, and ij is an ideal, we can say that F plus G is in ij, which then means that F plus G is an I. And then we can also say that since I sub I is an ideal, Rf is in I sub I, which is contained in I. So we have I is an additive subgroup that contains, or that satisfies absorption. So this is I is an ideal. Okay. So now since we know that I is an ideal, it's an ideal in our ring K, so we can apply Hilbert's basis theorem to get a finite basis for I. So now we can say that I equals the ideal generated by F1 to Fn for some F and I. Fi and I should say. Okay. So now what we can do is look at each of these particular F sub I, and we can say each of these guys has to be contained in one of the things in our union. So since it's only a finite number of things, we can take the biggest ideal that contains, if we just list one ideal containing each one of these, so we say Fi is in I sub j sub I, then we can take the max of the j sub I, that is the biggest ideal that we just listed here, and all of the Fi are going to be contained in I sub this max. So let's just call this n. And since they're all contained in In, that means that the entire ideal is contained in In. Because here we have the smallest ideal containing each of the F's, the union of all of them is the smallest ideal containing all of the F, and here we have another ideal containing all the F, and that's true for all of them. So for all of the ideals bigger than in, they all have to be equal to I. Okay, so that shows that our ring K satisfies the ascending chain condition, which it turns out is nice because you might see there's a connection between the conclusion of the Hilbert's basis theorem and this ascending chain condition. So now we're going to try and generalize this. We're going to take a step back a little bit, and we're going to talk about rings that aren't K. So in general, we have a name for rings that satisfy the ascending chain condition. They're called Noetherian. So you can have a definition here. And we say a ring R is called Noetherian if it satisfies the ascending chain condition. Or I'm just going to call it the ACC. Okay. So the reason this is such a nice property is because, like I hinted at before and you might have picked up on, is it is actually true that a ring is Noetherian if and only if all of its ideals are finitely generated. Which this is a really nice property to have. So this notion of Noetherian basically gives us a oftentimes way easier way of checking to see if all ideals in a ring are finitely generated. But we do still need to prove this. And this proof is actually, so if we split it into two directions, first we need to show that if a ring is finitely generated, then, or if all ideals in a ring are finitely generated, then the ring is Noetherian. And that's just going to be identical to our proof of the ascending chain condition for K, but instead of using Hilbert's basis theorem to get that all the ideals are finitely generated, and therefore I is finitely generated, we're going to use the fact that we're assuming that it's finitely generated. So finitely generated applies Noetherian, just following that proof, and I'm actually going to leave it as my exercise to prove the other direction, where a ring is Noetherian implies that all of its ideals are finitely generated. And the easiest way to do that is by contradiction. So you can assume that there is some ideal that's not finitely generated and show that that means that it's not Noetherian. Okay. So I'm not going to prove that. So one more kind of good thing to just note, but that I'm not going to talk about in much detail, is this lemma that kind of brings everything that we've talked about together, which is that a polynomial ring over a Noetherian ring is Noetherian. I'm not going to talk about this in too much detail, but I think it's good to mention because it can be helpful on, like, I think the tiers. But it also brings it full circle because you can see pretty easily that a field has to be Noetherian because it only has two ideals, the whole field itself and the trivial ideal. So all ascending chains are either finite number of zeros and then the field, or all the zeros. And in any of those three cases, the nested chain of ideals has to terminate. So fields are all Noetherian, So when we look at our polynomial ring over a field, it's definitely also Noetherian, giving us Hilbert's basis theorem, giving us the ascending chain condition. Okay. So now returning to our specific case of K, with that little divergence for a generalization, we can start to look at other properties of Gröbner bases, because that one property that we gave of Gröbner basis isn't like super useful. Like, it isn't all that often that you're trying to look at leading term ideals when you're just like working with a ring. Probably, I can't say I've done much work in ring theory, but okay. So one of the problems that was mentioned in the first presentation was the problem of the division algorithm on this ring K. So the issue is when you do the division algorithm by a set, the remainder wasn't unique. So if you had 3 functions that you want to divide by, you could get a different remainder depending on what order you divided the functions by. And you don't really want this. That makes it a pain to divide things. So one of the best properties of Gröbner bases is that basically this problem's fixed. So if we let I be an ideal, and let G be a Gröbner basis, I should say, then there is a unique, and F in K, then there exists unique R satisfying the 2 following properties. The first one, that no term of R is divisible by the leading terms of any of the GI, for any I, should say. And that there exists G and I such that F equals G plus R. Okay. So this basically is just telling us that the division algorithm by a set works as we would want if that set is a Gröbner basis. And if it's not a Gröbner basis, it won't necessarily work. Okay. So to prove this, we are going to use the division algorithm a little bit. So given F and K, we can divide by G. So first we want to show that just such an R exists. So that's why we're not worried about the uniqueness when we use the division algorithm. So just to show that something exists, we can still do that F equals G1Q1 plus G2Q2 all the way through to GTQT plus R. Okay. So by the properties of the division algorithm, the no term of R is divisible by the leading term of GI for any I. And also we have, if we call this big function G, then G is definitely an I because of absorption and additive subgroup. So we have that F equals G plus R for a G and I. So now we want to do the difficult thing, which is prove uniqueness. So to prove uniqueness, we're just going to assume that there are 2 R with these properties, R and R prime. And that would mean that F equals G plus R plus G prime plus R prime. Or sorry, equals, so F equals G plus R, which is also equal to G prime plus R prime by this second property, since we're assuming that 2 exist. And this tells us that R minus R prime equals G minus G prime. and g minus g prime, since g and g prime are both in I, is in I. So now we have that this r minus r prime is in I. Okay. So this tells us that the leading term of r minus r prime is contained in the ideal of leading terms of I, since r minus r prime is in I. Okay. Now this is where we do have to use the result from the previous presentation, which this tells us that the leading term of r minus r prime is divisible by the leading term of g sub I for some I. Which contradicts with the first property of R. So that gives us uniqueness. I should mention this actually follows from the fact that this is the ideal generated by the g sub I. Sorry. So basically, because this is an element in this ideal, we have a proposition that tells us that this is divisible by some of one of these leading terms. Okay. So that gives us our nice property about Gröbner basis. And a lot of the times this is actually used as the definition of a Gröbner basis, but the text I was using decided to do it the other way, and I think it's just because you build a lot of intuition thinking about it this way, I think. Okay. So this gives us a really nice way of solving another problem that we have with ideals, and that's the ideal membership problem. So given a function in this polynomial ring, it can be difficult to tell just by looking at it whether or not the function's in the ideal. But if we have a Gröbner basis for the ideal, then basically just by this property, since we know that the remainder is unique, we get that if f is in K, f is in I if and only if the division of f by a Gröbner basis of I gives remainder r equals 0. Okay, so it's pretty obvious that if r is 0, then the function is in I, since r is unique. And then if f is in I, then we know that f equals f plus 0. And then that second property of the Gröbner basis told us that there is only one r such that both of those things are true, basically. So the fact that this f is an I tells us that this r has to be 0 by that second property. Okay. And that gives us this ideal membership. Check. Still recording. Okay. So this brings us to the last thing I'm going to talk about, which is, I'm going to butcher the pronunciation. I couldn't find anything that would tell me how to pronounce it, but I think it's Buchberger's criterion and his algorithm. But to state this, so basically, the idea with this is we want to figure out how we can easily tell if some basis is a Gröbner basis or if it's not. Because we don't have a good way of actually figuring that out right now, aside from basically checking every function in the ring. Okay, So we're going to need to state a bunch of definitions before we can actually state the criterion. So first I'm just going to do that. So we have our first definition. And basically we are going to write f, lowercase f, over bar, capital F, to denote the remainder of the division of little f by big F. And it should be noted here that since f is not necessarily a Gröbner basis, f has to be an ordered set, basically, an ordered S-tuple. If f is in fact a Gröbner basis, then we can define this instead on a set instead of on an ordered S-tuple. But more generally, it's defined as a ordered S-tuple. I should say this is like F1 through Fs. And this isn't a set. Okay. The next definition is if we let F and G be in our ring K and non-zero, then we have, so this relies on a definition from last time, but basically we say the multi-degree, multi-deg, which this is multiplicative degree. It basically means what you would want it to. It's just the maximum, basically, power that's in the polynomial. It's the multiplicative degree. Okay, but if this is alpha and the multi-degree of G is beta, and then we let gamma be this ordered set, gamma 1 all the way through to gamma n, where gamma I is the max of alpha sub I and beta sub I, which would just be like the multiplicative degree of each variable, because remember we have n different variables in our ring. Okay. Then we define x to the gamma is the least common multiple of the leading monomial of f and the leading monomial of G. Also written as x to gamma equals LCM of LM of f and LM of G, which is leading monomial. Okay, now the last definition that we need to state the criterion is called the S polynomial. So we define the S polynomial of f and g, and the order does matter with this, is defined like this. S of f comma g equals x to the gamma over the leading term of f times f minus x to the gamma over the leading term of g times g. Okay. So using all these definitions, we can state the criterion. I'm not going to prove anything about the criterion. but it does yield one more nice result, and that'll be basically the end of it. Okay. So, now we can state this. Okay. So if we let I be a polynomial ideal, then a basis G, it is important that G is a basis, so I will write that, which is G1 to GT is a Gröbner basis of I if and only if for all pairs I not equal to J, the remainder on division of the S polynomial of Fi and Fj is 0. So this gives us a concrete way of figuring out whether or not a basis is a Gröbner basis. Now, you might be looking at this and saying, if there's like even 3 things in that basis, this is going to be a pain to compute. And you're right, but luckily we have computers, so we don't need to compute them. And that's what the main purpose of this is in addition to making this very easy for computers to check whether something's a Gröbner basis, it also yields an algorithm that lets us to compute a Gröbner basis, giving any basis. And basically the way that you do that is just by going through all of these pairs, computing the remainders, and then just any non-zero remainders, just tack them on to this set. And then if you keep doing that, you got to loop through it again, because now that you've added another thing in this set, you have a bunch of new pairs to check for remainders. But if you just keep doing that, it's actually guaranteed to terminate, and that's called Buchberger's algorithm. And that gives us a Gröbner basis. Given it's not a very efficient algorithm, there are a couple different ways that you can improve it. I'm not going to talk about those. It can take a lot of computing power, but in a lot of cases it's still very useful in itself, and a computer will be able to compute a Gröbner basis in some amount of time, just sometimes it's an unreasonable amount of time. So yeah, that's all that I have for you guys today. So thanks a ton for listening. I hope you guys have a good break, and hopefully I'll see you guys next semester.